Again, it's a red stick.
What is going on, guys? Welcome back to the Algorithms and Data Structures tutorial series. In today's episode, we're going to talk about the practical analysis of algorithms. So we're going to take the knowledge of the previous videos, so runtime complexities, big O notation, theta notation, important runtimes like constant time, linear time, quadratic time, and so on. We're going to take all that theoretical knowledge and put it to work. So we're going to look at two algorithms that are a little bit more complex than the algorithms that we talked about in the last few episodes, these sample algorithms. So we're going to look at two a little bit more complex algorithms and determine their exact runtime complexity. So let us get right into it. Now, before we get into the actual analysis of this algorithm that you can see here on the screen, I want to mention that this episode is going to be very mathematical. So it may be the case that your high school level math knowledge that I talked about in the first video may not be enough. However, the topics that are covered in this video are not essential, not mandatory, so you don't need to know all the mathematical operations that we're going to apply here. So in a sense, if you're not interested in the exact mathematical analysis of an algorithm, you can skip this episode or just watch it without understanding every single thing, and you can proceed watching the next videos. However, if you're interested in mathematics and you're at least familiar with the so-called sigma sum notation, which is this thing here, like sigma sum from I equals 0 to n of something. If you're familiar with this thing, this episode should be not necessarily easy, but understandable to you. So this is what we're going to need in this video, definitely. Now, let us look at this algorithm here. The algorithm here, we're not going to talk too much about its functionality because everything it's doing, or all it's doing, is essentially just adding numbers to k and then returning k. So in a sense, we're just adding, and then ending up with a value k that we return. But the question that we're asking here is, how many primitive operations do we have? So let's go ahead and naively just analyze the algorithm. We can say, okay, this k equals 0 is just one primitive operation. And then we have a loop, and the loop in and of itself is not necessarily a primitive operation. We could say it is, whatever. But the question here is, inside of this loop down here, or inside of this loop, first of all, we have another loop, but then we have a statement, which is also just one primitive operation, and the return is also one primitive operation. So to determine the amount of primitive operations, we need to figure out how many times this statement gets executed, because this statement is one primitive operation, okay? And this statement is also one primitive operation. We don't really care about these two because they're basically just a constant plus 2. So we can actually ignore them when it comes to the runtime complexity because they're not important. As you can see, this is one statement, another statement, then we have loops in between. So this statement here is interesting because the k plus j plus I statement gets executed as many times as these two loops are being executed, or as many times as these two loops iterate. So the first one is easy because we're starting I equals 1 and then we're going up to n. So we essentially have 1, 2, 3, blah, 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 up until n. So in a sense, this is just n times. We execute this loop n times. However, this statement gets executed more than n times because we don't execute it n times. We execute the loop that executes the statement n times. So this thing here gets executed n times, and how many times it gets executed itself. So how can we figure out how many times this loop gets executed? In a sense, we have just I plus 1 to n, but the I, and this is a tricky thing here, the I is constantly changing. We don't have a number like 4 and then we go up until n, but we have a constantly changing number. So the first time we go from 1 plus 1 is 2, 2 to n, then we have 3 to n, then we have 4 to n, and so on, until we get to I plus, or actually n plus 1 to n, which is actually over the limit, so we don't care about it. But how we can go about this is to write down the pattern. So what do we have? The first time we go from 2 to n, as we already said. So we have 2 to n. This is how many times this loop gets executed. One time, 2 to n times. What is this? This is essentially just n minus 1 times. Because this here, 1 to n is n times, we have n minus 1 times. Then we have 3 to n. 3 to n, means it gets executed n minus 2 times, and so on. So in a sense, we keep going like that until we get to n minus n times, because that is essentially just 0 times, which in a sense means that we're just executing this n minus 1 times plus n minus 2 times plus n minus 3 times, and so on, until we get to 3, 2, 1. This is the thing that we need to calculate. This also is already including this loop here, because in order to have this scaling up, have this I increasing so that we get to n minus 1, n minus 2, n minus 3, and so on, is because this loop here is iterating. So we have 2 loops, and in total, this statement gets executed that many times. I hope everything is on the screen here. But this is essentially what it is, right? So what we can do here to figure out what this actually means, because this right here is just, you know, a pattern. We cannot really say what the runtime complexity is based off of this thing. So what we need to do is we need to write it down in the sigma sum notation. And the sigma sum notation is essentially just saying, okay, we write the sigma symbol here, and then we say, okay, where are we starting? And we're starting at I equals 1, because obviously we're starting at I equals 1, as is stated in the loop here, and we go up until n. And what do? We always say n minus I. This sigma sum notation essentially means, if we write something down like that, it's exactly the same thing as here. So we say it's n minus I, and in the first iteration I is 1, so it's n minus 1, and then it's plus, so because it's the sum of all the individual parts. Then we say, okay, n minus I, and this time I increases by 1 because it's going towards n. So we have n minus 2, and so on. So this is the sum. And the beautiful thing about this sum here is that it can be rewritten in a different way. And this is the part where higher level maths come into play here. But we're not going to talk about these too much, because the tutorial series here is on algorithms and data structures, not on mathematics. So what we're going to do is we're just going to take this term here and put it into Wolfram Alpha. And you can see then what this means. So essentially we're just saying sum of n minus I equals 1 to n. This is how you write this down in Wolfram Alpha. And then this machine here, this computational intelligence, is going to return this statement to you. It's essentially just n minus 1 times n divided by 2. As you can see, n minus 1 times n divided by 2. So this is essentially it, and this is the runtime complexity. This is actually the actual amount of steps, the actual amount of primitive operations that we do, at least in this part here. So in this in these 2 for loops here, this is the amount of primitive operations that we do. Okay, we can add +2 at the end to get the total amount, but that is the exact number of primitive operations if we assume that this is one primitive operation and these loops are just running without any conditions that are also primitive operations or whatever. But even if there were, we can just go ahead and multiply by 3 or something, for example. Whatever, this is the exact amount. So in a sense, if we multiply this out, we get n squared minus n divided by 2. Divided by 2 is essentially just the constant factor 1/2, so we can just ignore it. And we have n squared minus n, and this leaves us with a runtime complexity that is in theta, so exactly n squared. So this algorithm here, we just analyzed it, has a quadratic runtime complexity. So an additional thing that we can do here, just in order to do some mathematical exercise here, is to come up with a formula for the return value and specify it in a theta notation. Now you might say that's not very useful, but it's actually something that I had to do in my college exam and exercises. So we're going to do it here as well, because it gives you an additional opportunity to practice your sigma sum and logical thinking skills. So what you do here is you analyze how does this return value k come into existence. Now in every iteration, or with each iteration here, we add j and I. And instead of looking at j and I combined, we're going to look at them separately. So to come up with k starts at 0. And then we always add a j and an I to it. We're going to start by analyzing the I value, because the I value is actually more simple. We already figured out that this second loop here runs n minus 1 times in total, then n minus 2 times in total, and so on. And with each n minus 1, n minus 2, with each n minus I, the I is obviously changing. So what we do here is we say essentially, when we have I equals 1, this loop runs n minus 1 times. So we have 1 times n minus 1 times. Then when I is 2, this loop runs 2 times, or actually not 2 times, but it runs n minus 2 times with I being the value. So in the first iteration here, in the first iteration of this loop here, in the first loop, the second loop runs n minus 1 times, and each of those times we add 1 as the I value to k. So we have n minus 1 times 1 added to k in the first iteration of this first loop here, of the outer loop. Then I gets increased by 1, it is 2, and we get into the second loop again n minus 2 times, and I has the value 2, so we add 2 n minus 2 times to k. And this continues on and on. So essentially we have every time I has a certain value, it gets added to k n minus I times. And this is exactly what we're going to write down in the sigma notation. So we can say sigma of I equals 1 up until n. We're essentially just saying it's I times n minus I. This is the amount of, or this is the part of the sum that we add to k when we just look at the I. So we have the j component here, and we have the I component here. And how many times do we add I? Or not actually how many times, but okay, let me rephrase it in a different way so that I don't confuse you too much. This thing here that we're calculating in the end, so whatever we get out here, is what happens by adding this I in this loop constellation here. So we're adding j and I, and if we ignore the j and we just look at the i's added over time, this is what we get, this notation here. And we can again go ahead and put this into Wolfram alpha. So this time it's not just n minus I, but it's I times n minus I. So like that. And this gives us the following formula. So n minus 1 times n plus 1, and this divided by 6. So n minus, or it's also fine like that, n times n minus 1 times n plus 1 divided by 6. Which is, again, we can just multiply this out, n squared minus n times n plus 1 divided by 6, and this is just n to the power of 3 plus n squared minus n squared minus n. So this cancels out, divided by 6, and we end up with n to the power of 3 minus n divided by 6. This is the actual number, the actual value that we get by adding these i's here. So we've covered that already. We're now going to look at the j part. Now the j part is a little bit more complicated because the amount of times we add j is the exact same that we add I, but j is constantly changing. And not only is it changing in the same way that I is changing, because I is changing only when this loop is iterating, j is changing in every single calculation. But we can look at it very simply. When I is 1, when I is 1, we start with 2, or we start at 2. So what happens is we add j, we have essentially the 2, we add j here one time as the value 2, so j has the value 2, it starts at 2, goes to n, and it gets added as 2. Then it gets added 3, 4, 5, and so on up until n. Then once this is done, once it's executed n minus 1 times, what happens is we increase I by 1, and we start counting at 3. So we have 3, 4, 5, and so on up until n. Then again, I gets increased by 1. We start counting at 4, or from 4, which means that we start here, 4 plus 5, and so on up until n. And as you can see, you can spot a pattern here. The value 2, j equals 2, happens only a single time. And this is the case when I equals 1. In the very first iteration of the second loop, when I equals 1, we add the number 2 to k, j equals 2 to k. This never happens again. Then we do the same thing for 3, 4, and so on. And then we increase I by 1. Then we add 3 one more time. So in total, 3 got added 2 times. 4 got added 3 times. If we continue like that, you'll see 5 gets added 4 times. And this is the exact pattern. So the J value, in a sense, if you spot the pattern and analyze it, you'll come up with the solution that the J value gets always added J minus 1 times. So if we have 2, 2 gets added 2 minus 1 times, which is 1 time. 3 gets added 3 minus 1 times, which is 2 times. So J is actually nothing but J minus 1, which looks similar like this one, but we don't have N minus J, but we have J minus 1. And this is the actual result for the J component of the sum. So J equals, now the question is, do we start at 1 or 2? I think we start at 2. Yes, of course we start at 2. Or actually, we could also start at 1, doesn't matter, because you would end up with 1 minus 1, which is 0, so it's actually the same sum. So J equals 2 up until N, and the expression here is J times J minus 1. And this again is something that we put into Wolfram Alpha, and J, actually we can do it with I as well, doesn't matter. We just have to remember for our own formula that it's J, so I minus 1, I equals 2 to N. And the result of this thing is the same, just divided by 3, so not by 6. So we have again N minus 1, N plus 1, divided by 3 this time. So we'll end up with the same expression here, which is N to the power of 3 minus N divided by 3, which again means that K is nothing but N to the power of 3 minus N divided by 6 plus N to the power of 3 minus N divided by 3. Now we could go ahead and multiply this by 2, so we would have N to the power of 3 minus N plus 2N to the power of 3 minus 2N divided by 6, and this in total would give us 3N to the power of 3, or 3N cubed, minus 3N, and I think we would be able to then just extract 3 and cancel it out, so we would end up with N to the power of 3 minus 3N divided by 2. This is the formula for the K value, so you could say that the K value is in, if you want to specify it like that. We had to do it in university, that's why I'm doing it. I don't really understand why this is important to specify theta notation, but essentially this would be in theta of N cubed. So cubic runtime. Not really runtime, but cubic mathematical expression, whatever. So I hope this was not too confusing. Now, for those of you who are still here and haven't given up yet, we're going to cover the second algorithm. I'm proud of you that you're still here. We're going to talk about algorithm B here. And algorithm B is a little bit different. It's not that complicated to analyze, but it might be a little bit tricky because you have to think of things of high school mathematics that you've maybe forgotten already. So it's a good exercise. So let's go ahead right into it and start analyzing the runtime complexity. So K equals 0 is again one primitive operation. I equals 2 to the power of N is one primitive operation. In here we have one primitive operation, and in the end we also have one primitive operation. Now the only question that we have here is how many times does this while loop iterate or execute? And this is a little bit harder to see directly because we don't have a full loop that tells us from I to N, which is obviously N times, or from I equals 0 to N. This time we have a starting value 2 to the power of N, and we want to get this value down to 0, or actually down to 0 or below. So this is the condition for the loop. We start at 2 to the power of N and we want to get to 0 or below. And what happens to I is we always have it. This is this line here. In this line, you can see that I gets halved every time. So it's divided by 2, divided by 2, divided by 2, and of course floored. So this mathematical sign here, if you don't know it, means floor, which means that you round the number down. So if you have something like 2.5, the floor function gets it to 2. If you have something like 3.76, it gets it down to 3. If you have something like 7.98, it gets it down to 7. This is the floor function. And this is what we're doing here all the time. So the question is, how many times do we need to have 2 or divide by 2 to the power of n in order to get to 0 or less? And this is actually not that difficult to figure out if you understand what a logarithm is. And the logarithm essentially is exactly the question that we're looking at. So let's look at the logarithm base 2 of a number x. The logarithm base 2 of a number x actually gives you a result, and this result is the amount of times that you have to divide to multiply 2 by itself to get to x. So if the result is y, the number of 2's that we have here is y. So put in a little bit more simple words, when we calculate the logarithm of a value to a certain base, it tells us how many times we need to multiply this base by itself in order to get there. So if you have 2 to the power of n, this doesn't mean anything else but 2 times 2 times 2 times 2 times 2, blah, 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 n times. This is the definition of 2 to the power of n, obviously. So this is n times. So the question is, how many times can we divide by 2 in order to get to 0? And the answer obviously is n plus 1. Because when you divide 2 to the power of n times, you get to 1. And if you divide 1 by 2, you get to 0.5. And if you get to 0.5, you essentially end up with the floor function rounding it down to 0. And even though we don't need to use the logarithm, in a sense, there is the logarithm in here, because what we're doing is we're asking, what is the logarithm base 2 of 2 to the power of n? And obviously it's n. This is essentially what we need to do to calculate the runtime complexity of this particular algorithm, because we want to know how many times can I divide a certain number in order to get it down to first 1, and if you then divide 1 by 2, you get to 0, because this question is asking how many times do I need to do it in order to get to 1, but we can then add one more time to get to 0. So this is the result here, n plus 1, which means that we have a runtime complexity of theta of n, linear runtime complexity for this algorithm here. Now, coming up with the formula for the return value is also not that difficult in this particular case, because the only thing we're doing is we're adding I squared. And I starts at 2 to the power of n and gets decreased or divided by 2, halved essentially, with each iteration. So what we do is we have 2 to the power of n, then we have 2 to the power of n minus 1, then we have 2 to the power of n minus 2, and so on until we get to 2, 1, and 0, which is essentially irrelevant. And what we're doing is we're constantly adding these things squared. So we have 2 to the power of n squared plus 2 to the power of n minus 1 squared plus 2 to the power of n minus 2 squared, and so on, 2 squared, 1 squared, and then 0 squared, which is nothing. And then we add all these things, and this is actually the formula for the return value. So put into different words, we have sigma I equals, let me think about this, we have 2 to the power of n minus, then 0, n minus I squared. This is the formula. We have 2 to the power of n minus I is constantly changing and increasing until we get to n minus n, which is 0, which is 1. And then we get, we take the result and square it. And this is the exact thing that we need to look at, so we're going to type it into Wolfram Alpha again. We have 2 to the power of n minus I, and the result squared. Let's do it like that. And we start at 0. And the result is 4 to the power of n plus 1 minus 1 divided by 3. 4 to the power of n plus 1 for n plus 1, was it minus 1? Yeah, divided by 3. This is the formula for the return value, the runtime complexity in a sense. For the return value, it's not a runtime complexity, it's the complexity of the return value, you could say the size of the return value. And actually that's maybe the reason you specify the theta notation, to know how big it gets, to have a size complexity in a sense. And we can just ignore the divided by 3, we can ignore the 1, and 4 to the power of n plus 1 is essentially nothing but 4 times 4 to the power of n, which means this is a constant factor that we can ignore, which means that we have an exponential complexity here, because we have theta of 4 to the power of n, and 4 to the power of n is exponential complexity, size complexity in this case of the return value. So that's it for today's episode about analyzing algorithms. I hope it was not too confusing to you. And as I said, if you don't understand everything, or you're not that interested in the deep mathematical analysis of algorithms, you can sort of skip this episode. You don't have to ignore it completely. You should know what it's about. You should know how to analyze algorithms. But maybe you're just here to get an intuition of different algorithms, data structures, then this episode might not be as interesting to you. However, if you're going to university, to college, and you have an algorithms and data structures course, you might want to know more of the mathematical details as well. And you also want to memorize or understand how to transform the sigma notation into the actual formulas by hand, or, I usually just memorize them because you cannot use Wolfram Alpha in your exams. However, this was a very practical episode of algorithmic analysis. If you liked it, let me know by hitting the like button and leaving a comment in the comment section down below. And also, if you haven't done it yet, subscribe to this channel to see more future videos for free. Other than that, thank you very much for watching. See you in the next video, and bye.